Welcome AP back to chapter 16. We just saw the video 16.6 on weak acids. Well, let's do now weak bases. Before we get to weak bases, let's review 16.6 because it's a lot of information for you to process. We have hypochlorous acid, weak acid. Okay, even tells you right there, weak monoprotic acid, reacts with water. So this is your acid, this is your base. Which means your base is going to turn into the conjugate acid and the acid into the conjugate base. We want pH if we're giving an initial concentration of the acid and we're giving Ka. So remember with Kas, you're only giving Kas with weak acids. Okay? So let's see if we get the answer that we're supposed to get. So step number one, we always need an equation, which we got it up there. Okay? You don't have to write it again. We are going to start with the initial of 0.10 molarity. And because water is a liquid, we don't need to worry about it. So we usually just draw a line underneath it. I don't have any products in the beginning. And I don't know what it changed by. So remember with our reactants, we're disappearing as our products are appearing. So 0.10 minus x and then x and x. So after you have your first equation, okay, so I'm going to put right here, I'm going to put some numbers, okay. So step number one, and then step number two, your ice chart. And then step number three, always write a Ka expression. So remember Ka is our products, H3O over our reactants. And the only reactant we care about is that acid. And it did tell us that we have x squared over 0.10 minus x, and it says the Ka is 3.0 to the negative 8. Now, that Ka value is very, very, very small. As you see that exponent, negative 8. So we can make an assumption, so we can avoid the quadratic. We can assume that x is so small compared to that initial concentration that it's just going to not matter. So then we have x squared over 0.10 equals that 3.0 times 10 to the 8th. Okay, well, let's plug and chug. All right, so get those calculators. 3.0, hit your E button, negative 8 times 0.10. Well, it should be about the same value, just a different exponent. So 3.0 times 10 to the negative 9, x squared. And we're going to take the square root of both sides. So square root. And we're going to get x equals, looks like 2 sig figs. So 5.5 times 10 to the negative 5th m. And what does that equal? Well, that equals my x's. Okay, so that's what they equal. So that equals my hydronium. And it equals that conjugate base. Okay, don't put the word and. Okay, put it equal because it shows that all two values equal 5.5 to the negative 5. Well, there you go, step number 3, okay? Step number 4, set up your expression. Find your x, but if you're going to make an assumption, okay, find your x, you need to check your assumption. So before you can even think about pH, okay, we need to check our assumption, which is called percent ionization. So percent ionization, you have an equation, and you can abbreviate it, percent ionization. It is that hydronium, or you could say H+. I'm saying hydronium because my balance equation said hydronium at equilibrium over that initial acid. Oops, concentration. Times 100. So to check, I'm putting some notes here, check assumption. When you check your assumption, it's called percent ionization. And you're trying to get less than 5%. That's a good assumption. So at equilibrium, we had 5.5 to the negative 5 over 0.1 times 100. We want these molarities to cancel and plug it in. 5.5, E button, negative 5, divide 0.10 times 100. I know it's going to work because that exponent is so small, it's not going to have hardly any factor. So that percent ionization, which matches our answer, that means, okay, how much the acid dissociates in water. This guy hit water and you barely had a crumb come off that water, okay? So now that our assumption is valid, now we can actually, oops, number 7, find pH. Well, pH is negative log of hydronium. So you're probably thinking to yourself, well, what if that percentage is higher than 5? You can't make the assumption. You got to do the quadratic, which we already know there is no quadratic equation on the AP test. So we're going to take the negative log of that 5.5 to the negative 5. And I know my answer should be somewhere around 5 because of that exponent. So negative log 5.5, E button negative 5. And 2 sig figs, I'm going to get about 4.3. This should make sense because remember, this was an acid that just hit water, okay? And according to our answer, 4.3. There it is, okay? If you can do weak acids, you can do weak bases, okay? And a solution of a weak base at equilibrium, that just means that this base doesn't completely dissociate in water. So remember Bronsted-Lowry, the base always accepts the protons from the substance, okay? So we have what's called a Kb for the base dissociation constant. So if I have this base, the water must be the acid, so that just means one of these protons is coming over, and I'm going to get my base with now a positive charge because of that hydrogen, and then I'll get my OH. So my base turns into my conjugate acid, and my water turns into the conjugate base. And remember, OH, that is the highest concentration for a base. When you're doing an equation for a base, it is mandatory. You have to add the water to the balance equation. When you do an acid, a weak acid, it's not mandatory. So this water right here, it's optional. You don't have to if you don't want to, okay? Only if they want to see who's the conjugate acid and conjugate base, okay? That is your choice. But for a base, you have to, okay? Because the problem is this, if you don't, where the heck did the oxygen come from? Because it didn't come from ammonia, it had to come from the water. So one of those protons is going to come over to ammonia. I'm going to get my ammonium and my hydroxide. And then my Kb, products of the reactants. Okay, and remember, no water in our Kb expression. Well, ladies and gentlemen, if you can do a weak acid, you can do a weak base. Okay, so let's try one. The larger the Kb, the stronger the base. So when you're looking at factors for your Kb, in our chart for Kbs, there's really not that many Kb values. You're looking at -1 or -2, -3. Those are very, very strong, weak bases. Okay, remember this is only for weak bases. So percent ionization for weak bases, it relates equilibrium of OH. So then for OH, we can get to POH, and then we can subtract 14 to get to pH. Okay, whichever way AP wants us to go. Notice the percent ionization for an acid is different for a base. So for an acid, it was hydrogen or hydronium at equilibrium, same thing here, over the concentration of the acid originally. Same thing, but now it's hydroxide. And why? Because when you're solving for hydroxide, you're solving for an X. So in your ice chart, this OH, that's going to be your X in your ice chart. Okay? Same thing. We want less than 5% because that's a good assumption. Okay, I'm going to set you up on number 2, but you're going to finish it. Okay, I gave you the answer. So we have ammonia. So we know our equation from above. Ammonia. I'm going to add my water. Equilibrium. And then I'm going to get my ammonium and my hydroxide. Okay, so I do want to calculate the concentration of OH. If my ammonia is 0.15 initially, and I do have a Kb value for ammonia, okay? So Step number 1, you have your balance equation. Number 2, let's do our ice chart. Initially, I don't have any products, so I'm going to lose some reactants, gain some products. And then that's going to set up my Kb expression. So my Kb, my ammonium, and my hydroxide. So I know my Kb, 1.8 to the negative 5, equals x squared over 0.15. And then I'm telling AP that x is so small to that 0.15, it's not going to matter. So I want you to solve for x. Okay, oops, I forgot the word assumption. Don't forget the word assumption. Solve for your x. And remember that x is going to equal OH and hydronium. But we can't say this is the answer yet till we check our assumption. So we usually tell AP, check the assumption, check ionization, okay? Because I didn't ask you to solve for it down here, but we have to check it anyways. So remember, when you're setting up this equation, okay, the OH at equilibrium, whatever that OH may be, over the initial base. Well, you can't put the word base. You got to actually put who the base is, times 100, okay? So finish it up. If you do it right, you should get this 1.6 to the negative 3, okay? See you on the next one.